This is the third lecture in the background math chapter for ECE 343 Signals and Systems. Last time we were taking a look at partial fraction expansions. In that particular case, we looked at rational functions where the roots in the denominator were all unique. We called those roots something like lambda, and so each one of the ones that were found in the denominator were unique, and so the methods worked for that particular case. We're going to look at what happens when you have a root that is repeated. So that would be a root, for example, lambda repeated r times. We'll just designate that lambda raised to the r. So in this particular case, you're going to need to modify the nature of the partial fraction expansion and the way you get the coefficients because of that repetition of the root. For repeated factors, the method of residues requires adjustment then. We're going to go ahead and look at the case where we have a root lambda. It's going to be repeated r times. And what that means is that the denominator has some sort of factor like this. You would have an x minus lambda raised to the r power. The corresponding terms of the partial fraction expansion just associated with that repeated root, there could be other roots. Those other roots would have just standard terms like we'd seen before. But for this repeated root, we need r different terms, and they all need to be different. And the way they end up looking is you end up having that root repeated r times. That's this x minus lambda raised to the r. And then we also get terms for a continuous reduction in the order of that denominator. So x minus lambda to the r minus 1, keep reducing it down until you have just an x minus lambda. And then the numerators of all those partial fraction expansion pieces are just constants. And the book calls these guys a's, little a's. They subscript them a0 all the way up through ar minus 1 for a total of r terms. The book doesn't use this tilde notation that I've introduced here, so I'm going to look at these upper coefficients, the numerator coefficients of this partial fraction expansion terms for the case of repeated roots, and I'm going to call them not a sub something, I'm going to call them a tilde sub. I use the tilde to avoid confusion with the coefficients a0 through whatever that were part of that denominator polynomial a of x that came from our original rational function fx equaling bx over ax. So the book kind of uses two different cases of using that notation. I think it's easy to get confused. So these are different A's, and I just want to make sure that we recognize them as different. So I'm going to call them A tildes. The coefficient A tilde then are found according to a formula that's a little more complicated. It's going to be something like A tilde sub I, right? And we're going to get a 1 over I factorial, and then we're going to take the ith derivative with respect to that variable x of the quantity, take that repeated root x minus lambda to the r times our original function f sub x, do all that math, and then evaluate at x equaling lambda. We're going to do that for the subscripts I equaling 0 to r minus 1. That's a total of r terms because the root is repeated r times. I would encourage you to think why this particular formula works. And I think the way you can tell is you can go ahead and sub what the partial fraction expansion is doing. We know we have that f of x and it's going to have all of those terms in there, right? And go ahead and apply that operator to that expression and see what happens. See what happens on there. What you will find is that when you are working with the coefficient little I, that is the only term that persists or remains on the right-hand side. So if I looked at it over on the other side, you're going to have some ith term in there somewhere. When we do all these derivative type operations and then evaluate, all the other stuff is going to disappear. You're only going to be left with that a tilde sub I, and then you're going to have some other stuff on the left-hand side so that you can find out what the value is. Not difficult to show, but something that would be worth your time to do so. I would also note that this modified expression for finding these coefficients a sub tilde also work for the case of simple roots or non-repeated roots. You could call that the r equaling 1 case, so a root of just single occurrence. And what we get is exactly the same expression that we had previously when we did the method of residues. So if you really want to just be general in all ways, go ahead and remember this modified form for finding these coefficients, which also works for the case of simple roots as well. Let's go ahead and show this by an example. And so I'm going to pick a pretty simple example in this particular case. I'm going to look at an f of x equaling 2x plus 1 over an x minus 1 quantity squared. So I think when we look at the denominator there, we can clearly see that we have a root at x equaling 1, but it occurs 2 times over, right, because of that squared in the denominator. So I have a root lambda equaling 1 repeated for a total of 2 times. In this particular case, the rational function is strictly proper. The order of the numerator is less than the order of the denominator, so we don't have to do any long division or anything like that to get direct terms. We're ready to just do our regular partial fraction expansion. Because it only has repeated roots, we only have to worry about the repeated root terms. If there had been other roots, we would have had them show up as well. Since we're focusing on the repeated root math in case, we'll go ahead and just deal with this very simple one. So I have an x minus 1 squared, right? And we know that the terms then are going to be a something over x minus 1 squared and then plus something over x minus 1. You might wonder at this point what this is really achieving because it seems like it's pretty simple on the left hand. What you'll notice though is that the numerator, right, is not just a simple constant. The numerator has a polynomial in it. And this partial fraction expansion gets us into terms, right? It gets us into terms. This term over here, the something over x minus 1 squared, and this other term, the something over x minus 1, the numerators of those have no x's. And so they are fundamentally a simpler building block set than the original partial or the original rational function. So let's go ahead and find these coefficients, a sub 0 tilde and a sub 1 tilde as well, so that we can complete this partial fraction expansion for the case of a repeated root. In this case, we have a repeated root that occurs a total of 2 times. So a tilde sub 0, right? If we go ahead and just look back at what our original expression was, it says we should have 1 over I factorial. I in this case is 0, so we're going to have 1 over 0 factorial. That's just going to be a 1. We're going to take the 0th derivative. That's just leaving the function alone. And then we're going to take that repeated root times the original rational function and evaluate at the root. So coming back down here and taking a look at this particular case, a tilde sub 0, we're going to have 1 over 0 factorial. That's that first term in there. That should evaluate to 1. The 0th derivative, I've written this out explicitly just so you know that we are doing it. I think when you get to doing quite a few of these, you probably aren't going to write d0, dx0 because you know that that just means leave it alone. So as you get a little more proficient here, you probably don't have to explicitly show all these kind of boring, trivial pieces, but we'll do it here for completeness sake. We had our original f sub x, right? We saw that up here, f sub x equals 2x plus 1 over x minus 1 squared. And then we needed to multiply that by that repeated root x minus 1 squared. You'll notice here what happens. Those guys cancel in there. Because it's the 0th derivative, we're going to leave it alone. And we have 2x plus 1. That's this final result down here, 2x plus 1. And we have to evaluate at what? At the root. And the root here in this case was x equaling 1. Put x equaling 1 into the expression 2x plus 1. I'm going to get 2 times 1 plus 1. That's going to give me a value of 3. So that a tilde sub 0 should give me a coefficient or a computed value of 3. I'm going to apply the same procedure, right, for this a tilde sub 1. Now the subscript I is 1, so I'm going to get 1 over 1 factorial as the lead coefficient. I'm going to need to take the first derivative with respect to x, right, of that expression. Again, we had f of x, that's the 2x plus 1 over x minus 1 squared. We're going to multiply it by that repeated root, x minus 1 squared, right, and then we're going to have to differentiate it. And then after all of that is done, we're going to go ahead and evaluate at the root location x equaling 1. So that first lead coefficient, 1 over 1 factorial, is just 1. We're going to take the derivative, first derivative of, well, we're going to get some cancellations in here just like we did before. In fact, once you've done it for one coefficient, that interior expression is always the same. You're just going to be differentiating that guy at different levels. In this particular case, then I need ddx of 2x plus 1. I need to take the first derivative of a simple linear polynomial expression. We know how to differentiate that guy. The derivative of 2x plus 1 with respect to x is just 2. So I'm going to get that derivative as being, whoops, let's go ahead and make that as a highlighter value. That's going to be 2, right? And we need to evaluate it at x equals 1. It seems a little redundant or kind of silly at this point to have this as being evaluated at x equals 1 because there's no x's present. That's okay. If there's no x's present, you don't have any substitution to do, and you're just going to end up with a value 2. So that second coefficient, right, that a tilde sub 1 is gotten a value of 2. If I put this all together, I get my final partial fraction expansion. There's the original rational function. This is my f of x, 2x plus 1 over x minus 1 quantity squared. And I know the partial fraction wants to break this up into a sum of simpler pieces. These pieces, because of the replication of the root, aren't just simple single order terms in the denominator. We need to handle that replication. So we get an x minus 1 squared in the denominator of one of the terms. There's just an x minus 1 to the 1 power as the other one. But the numerators are definitely more simple because there's no x's up there. We had computed those out as 3 and 2. Now, if I wanted to verify that this indeed was an appropriate, or it was actually doing an equivalent representation of my original function, I could easily do it in this case. I could take this right-hand term and multiply it by x minus 1 over x minus 1. That doesn't change anything, right? That's just like multiplying by 1. Why would I do that? Because now I have a common denominator, so both of these terms are going to have an x minus 1 squared, right? And then I just would add up the numerator terms. If you look at the first one, it had a 3, right? And over here, I had a 2 times minus 1. So I'm going to have a 3 minus 2. It's just going to be a 1 in there. And then I also had a 2x in there, so I'm going to have a 2x. So just by finding a common denominator and recombining the numerator terms, I see that this whole thing, it evaluates to 2x plus 1 over x minus 1 quantity squared, which was my original f of x, absolutely equivalent. As you're first doing some of these partial fraction expansions, if you're a little rusty or a little unsure of the process, you might consider going ahead and re-expanding things out and making sure that they are truly equivalent. This is a step that might be particularly important if you didn't start originally with a strictly proper rational function. I think a lot of people could catch some errors in those cases by just re-expanding out and making sure that what they got was an equivalent expression. Okay, so something else that you might do as well is you might check out MATLAB's residue command. So if you do help residue in the MATLAB command line, it'll tell you all about the residue function. The residue function basically does a partial fraction expansion for you, and it allows you to check your hand calculations. I still want you to be able to do a hand calculation. You should be able to do these by hand. You should understand the process that's involved in doing a partial fraction expansion. But if you're sitting there on a homework and you're wondering whether or not you did it right, that MATLAB residue command makes a really easy way of checking out your result. You should be able to know for certainty that you did the partial fraction expansion correctly. There's also a roots command in MATLAB. Roots command allows you to root out a polynomial and find its factors or its roots. We know that this is a necessary step as part of the partial fraction expansion. Once we had a strictly proper rational function, the next step was to root out the denominator so we know what each piece of that expansion is. And so the roots command can certainly help you out, especially if the order of the polynomial is greater than 2, right? I expect everybody can find the root of a first order polynomial or a quadratic equation. But once we get to cubics and higher, it definitely is hard to do by hand. And I think it's absolutely appropriate that you use a computing technology to find those roots. Even with a quadratic, you could use roots just to verify your answer very quickly. I would note that polynomials with real coefficients, we are going to encounter these for the most part. This is the most common case that we're going to see in this class, that when we look at some particular function, right, if we look at some f of x being equal to some bx over some ax, that's our rational function, right? If the polynomials here, the things that make up that ax and that bx, have real coefficients, right, they can still have real or complex roots. It is possible, even though the coefficients of the expanded form polynomial are all real, that you could still end up with complex roots. However, if the original expanded polynomial all had real coefficients, those roots, if they are complex, must occur in complex conjugate pairs. So if, right, a root is complex coming out of a polynomial with real coefficients, the conjugate value must also be a root. So roots from real valued polynomials, right, or real valued coefficiented polynomials must come in conjugate pairs. What you might see then is something like this. You might have something like an x minus j. That's a root at what? J. If that was the case, you would also have to have a root at the conjugate location, x plus j. One way that you might get an idea of why that is, multiply that out. What do I get? I get an x squared. I get a minus jx plus jx. So those guys cancel, and I'm going to have a minus j times j. That's going to be a plus 1. That result there is got coefficients that are all purely real. If you didn't get that kind of cancellation going on from the conjugate nature of those roots, you could end up with coefficients that were not real valued. So something that you can play with a little bit. I will say that when you have complex roots and they come in conjugate pairs, as is the case of rational functions where the coefficients of the polynomials are real, um, it oftentimes some people have a preference for keeping those conjugate roots together, and then they do the PFE such that it has quadratic terms. So, for example, if we knew that we had a root, a complex root lambda, that's at x minus lambda. If it came from a rational function that had all real coefficients, we know that there's also going to be the conjugate root, x minus lambda squared. If you multiply those guys out, you'll get a little quadratic term, and those coefficients, little a1 and little a2, are all going to be real valued, so you don't have to mess with j's in that particular case. If we left things in a quadratic form, the numerator is allowed to have a little x term in there. It's going to be a c1 x plus c2, and that's oftentimes how people leave it. So where are we going to mostly use these ideas of partial fraction expansions? Later on, when we get to transform domain and we start doing Laplace transforms or Z transforms, we're going to find out that in order to do an inverse transform, we are going to utilize tables for that, and those tables are based on really simple pieces. And if you didn't have simple pieces to begin with, you need to do things like a partial fraction expansion to get those simple pieces so you can do the invert transform. You should have seen that before in a circuits class. Some people like to work with those quadratic terms, and those quadratic terms are found in the Laplace transform table, so it is possible. I personally find it easier just to go ahead and work with the complex roots and keep it all simple in terms of first order factors. So I generally myself do not go down this quadratic path. I just find that less obvious and less simple. I'd rather just deal with the complex roots as simple single roots. But some people just have an aversion to complex numbers, and so they prefer to work with quadratics. It's really a matter of personal preference. There is the techniques of this laid out in the book, talking about how you can find those coefficients C1, C2. So if that's something that appeals to you, go ahead and take a look at it. We're going to switch gears now, and we're going to be dealing with really the last part of the background chapter, and that is something that deals with vectors, matrices, and some basic linear algebra techniques. There's no way that we can do this topic justice in half a lecture, so it's absolutely going to have to be ultra brief. So this is a really brief review of the core concepts in vectors, matrices, and linear algebra. I won't say that this class necessarily demands, a huge amount of sophisticated or even a lot of use of things like linear algebra, concepts. But there are definitely times when using a vector notation can be handy and helpful, and there are occasions when we need to use some linear algebra math. I think that as you go and start plotting out signals that involve a lot of values of the independent variable, adopting a vector type notation makes that much more simple. And so we probably should have a reasonable idea of these basic vector matrix and linear algebra language and techniques. So let's quickly go through a review on that as well. A vector is a collection of objects that is really one-dimensional, if you will. So there's a collection of some number of objects, maybe the number of objects is n or m, and we just need to stack them up together. There's two conventions typically for writing out vectors. There is a thing called a column vector, which I've shown over here. So I've got this column vector, and it looks like a column, right? So we got this big column sitting in there. We stack these objects one on top of one another so that it makes a vertical stack. In this particular case, there are n rows and there is a single column. It's called a column vector because there's only one column, okay? We usually denote the dimensions or the size of that vector by indicating the number of rows and then the number of columns. So with a column vector, it's going to have some number, right, for the total number of elements by 1 because it's a single column structure. So this would be an n by 1 vector x. That makes a column vector. We could also do a row vector. We could express a collection of objects not as a stack vertically, but we could stack them out horizontally. So this time the thing goes along a row. So these are called a row vector. In our convention of how we indicate the size of this, there's a single row, and then there's however many objects. I'm going to call it m here. There's going to be m objects in here. So this is a 1 by m, right, vector, something along those lines. A matrix is just a two-dimensional vector, or you could think of it as a vector as being a one-dimensional matrix. A matrix is going to have a number of columns and a number of rows. So here I've drawn out a matrix A. I've allowed it to have n rows, and I've had the number of columns be somewhat different at m. So this is an n by m structure, right? I have n total rows and I've got m total columns. If I counted the number of rows in here, right, there's the first row, go all the way down, and this one down here is the nth row. If I counted the number of columns, here's the first column, and we're going to go across all the way out to the nth column. And we do start first row, first column in the upper left in this particular case. I went ahead and showed that the element in there, this whole thing was called cap A, that's cap matrix, that matrix is cap A, and it's comprised of elements little a's. And I've subscripted them so that you know where they are in the structure. So A sub 1, 1 is in the first row, first column location, right? And we could go all the way down to the lower right. That's the A sub nm. It's in the nth row, nth column, something along those lines. If you wanted to know the total number of objects in this, right, it's just n times m because it's a rectangular structure. So matrices are rectangular in configuration. Vectors are just special cases of matrices. I think we can all appreciate that. If you let n be equal to 1, you end up with a row vector. If you let m be equal to 1, you end up with a column vector. Some matrix language and concepts are in order now. So let's go ahead and take a look at some of those. And I'm going to illustrate most of these by examples. It just will be more efficient that way. So there is something called the transpose operator. We can denote that by taking some object. I've shown a vector object in this particular case. We could also take the transpose of a matrix, but take some object, a vector or matrix, and if I want to transpose it, I'm just going to denote that by a superscript t. So a transpose here, x raised to the t if you want to call it, or xt, this would be read as the transpose of x. We can show this by some examples. Suppose I have a row vector, 3 elements, and I'm just going to let the elements be 1, 2, and 3, and I transpose that. That's going to turn that row vector into a column vector. It's still going to keep its 3 elements, right? It's still going to keep their order, 1, 2, 3, right? It's just going to change or alter its orientation from row to column. We could take a column vector, for example, this 2-element column vector that goes with elements 4 and 5. I can transpose that, and that's going to make it into a row vector that's going to have those same elements. It doesn't change the elements inside it. It just changes their orientation. Rows become columns, essentially. If I do this to a matrix, and this is probably better because it shows more of the total process going on in here, I'm going to have in this particular case a 6-element matrix. What's the dimensions on this? We should be able to get it pretty quick. We know we do row first, right? And there are 2 rows and there are 3 columns. That's the second one. So this is a 2 by 3 matrix. I'm going to go ahead and give this guy a series of elements, 1, 2, 3, 4, 5, 6. And I'm going to transpose it. When I transpose it, the rows become columns, and the columns become rows, if you will. And so in this particular case, 1, 2, 3, that top one, right? That's that top row becomes the first column, 1, 2, 3. The second one, 4, 5, 6, that's the second row, becomes the second column, 4, 5, 6, something along those lines. So transpose, pretty easy. It just swaps the orientation. It swaps rows with columns. A diagonal matrix is one way of describing it is by starting with a vector and then just saying make a matrix out of that set of elements. So if I think about a diagonal matrix made from the vector 1, 2, 3, we're going to end up, what was that vector 1, 2, 3? I've written this particular one as a row vector. It's a 1 by 3 for a total of 3 element structure. Making it into a diagonal matrix is going to make it into a square matrix where the main diagonal has those elements, right, from the original vector. So I'm going to see that 1, 2, 3 just along the main diagonal, 1, 2, 3, and there's going to be zeros everywhere else. Diagonal matrices are square and equal to their own transpose. There is something called an identity matrix. An identity matrix is just a special case diagonal matrix where all of the elements are 1. So if you have a diagonal matrix of all 1s, we will identify that or call it an identity matrix. I've given an example here of I3. I subscripted that 3 just so you know the dimensionality of it. This is a 3 by 3 identity matrix. It has 1s on the main diagonals and zeros everywhere else. This identity matrix is nice because if you multiply a matrix by an appropriate identity matrix, you'll get back the same matrix. That's why they call it an identity matrix, because it provides you the multiplicative identity from linear algebra. You take something times that identity matrix and you get back the something. A symmetric matrix is a matrix that is equal to its own transpose. This, of course, requires that the original matrix be square, right? Otherwise, you wouldn't be able to get equivalence of those two guys. So I'm going to give an example here about as small as it can possibly get and still show the concept. I'm showing a matrix A here, which is a 2 by 2, 2 rows, 2 columns, so it is square. I'm going to have it have a column or overall elements 1, 3, 3, 2, something along those lines. And I notice that if I transpose that guy, I get exactly the same thing, right? I'm going to take this row 1, 3, and it becomes a column that would go this way 1, 3. If I took the second one, that would be that row 3, 2, and then it becomes a column that becomes that 3, 2. It's equal to its own transpose. So since A is equal to A transpose, I know it to be a symmetric matrix. These are properties of some of these basic objects that we see in linear algebra, and these properties end up usually helping us, and they help us do operations more efficiently or to better understand operation. You should remember from your linear algebra class that there's something called a determinant. A determinant takes a matrix and reduces it down basically to a single number. There's lots of applications of determinant. We'll see one later when we talk about Cramer's rule. But a determinant and it has to be a square matrix, results in a scalar value. I'm going to show this for a 2 by 2 and a 3 by 3. Much beyond that, it starts getting really kind of not fun to compute out things like determinants. You have to break things down into a bunch of cofactors, and it just can get very complicated quick. I think you should be able to handle hand calculations of determinants for up to 3 by 3 matrices. So if that's something that you don't remember all the rules in there, you might do a little bit of a refresher. I'll try to kind of remind you of some of it. So in this particular case, I'm going to look at a matrix A. I'm going to let it still be that 1, 3, 3, 2, and I'd like to find its determinant. How do we find the determinant of a 2 by 2? I take the first main diagonal 1 and 2, right, and I multiply those two elements together. That's this guy. And then I'm going to subtract off the product of the other diagonal that's in that matrix going the other direction from lower left to upper right. And so that's going to be minus a 3 times 3. So I'm going to get 2 minus 9 is going to be minus 7. That minus 7 is the determinant of A. It is a scalar value. By the way, if you wanted to verify a lot of these things, you can easily do it in MATLAB. Let's go back up just for fun and take a look at a couple of these ideas. So we looked at all these basic objects, and then we started talking some operations. Transpose, for example. If in MATLAB I had an object X and I wanted to transpose it, if I put a dot prime on that guy, it will do a transpose on that. A diagonal matrix, if I wanted to create a diagonal matrix from a vector, MATLAB has a diag instruction just like that. So you can take that diag and make it into a full matrix that is just a diagonal matrix. Identity matrix, they're certainly built in MATLAB things. They're easy to produce. You could just take a diag of a column of ones or a row vector of ones, so I won't necessarily worry about that. Symmetric matrices are just a property with transpose, which we already know how to do in MATLAB now. We're down to this idea of a determinant. MATLAB has a command called det. So if I do det of A, that's just shorthand for determinant of A. So if you defined in MATLAB an object that was a matrix with elements 1, 3, 3, 2, and then you did det A on that guy, you would absolutely get out of there minus 7. So you could easily verify this hand calculation. If you're still trying to remind yourself of the mathematics of linear algebra and the like, and are just a little bit maybe rusty on those things, I definitely would encourage you to go in and use MATLAB to verify your hand calculations. Let's do a determinant for a larger matrix, a 3 by 3. So in this particular case, this is one of those ones where we're going to break it up by cofactors again. So I'm going to take this first element 1. You might have, I hope, remember this from your linear algebra days. And so I'm going to get rid of the first row and the first column, and then I'm left with that little matrix down there. And I'm going to find the determinant of that smaller matrix, and I'm going to multiply it by 1. So I'm going to have 1, right, because I started right there up in the upper left. That's where I'd always start. And then I'm going to take the determinant of the smaller matrix that results by eliminating both the row and column of the element that I started out with. So in this particular case, I'm going to take 3 times 7 minus 6 times 4. So I get 3 times 7 minus 6 times 4. That's the first part of this calculation of the determinant. Then I move over. I need to work my way across this entire row. So I'm going to move over to the next element, that's a 0, right? Now I'm going to get rid of, I'm going to do this in yellow, I'm going to get rid of this second column in the first row, and I'm left with a matrix that is going to be 0, 4, 5, 7. So I'm going to get 0 times, and I'm going to get what, 0 times 7 over here. Let's do that in a different color. Maybe I'll leave it as red. So I'm going to get 0 times 7, something along those lines, and then subtract and do the opposite diagonal of 5 times 4, something like that. Because the lead coefficient was 0 there, you wouldn't have had to gone through and done all this calculation. I did that for completeness, trying to make sure that you saw where all the terms are coming from. Do notice that there was a sign change here. As you move over from one element to the next, the sign just sits there and flip-flops back and forth. We're not going to prove this. That's really the job of your linear algebra classes, so that's something that you should have been going through when you took that math class, which is part of the prereqs to this course. To finish this out, then, we need to go over to that last element in the row. So our next factor to multiply is going to be a 2. That's that 2 out here. And what am I left with? Let's actually do this in blue just so we can kind of see that as well. I'm going to get rid of that last column and get rid of this first row. That leaves me a vector or a matrix over here, 0, 3, 5, 6. And I need to find its determinant. So I can have 0 times 6, that's the main diagonal, minus the off diagonal. So the product of the off diagonal elements, 5 times 3. So I'm going to get minus 15 times 2 is minus 30, add it to the other piece, and I end up getting minus 33 as the determinant of this matrix. Again, this would be very easy to demonstrate in MATLAB. You can, in MATLAB, quickly identify or define this matrix A. Let's go ahead and show what the code would look like for that. I'm going to move this up just a little bit. If I wanted to define a matrix A with that original set, I would say A equals, I'd use a square bracket because I'm trying to define this matrix. I'm going to start by providing the first row. So I'm going to say 1, give a space, 0, give a space, give it 2. I'm going to put a semicolon. That just means go down to the next row. And then I'm going to go a 0, 3, 4, semicolon, go down to the next row, right? 5, 6, 7. Ended out with another square bracket. That would define this object A, and if you went ahead and typed that into MATLAB, you'd see MATLAB spit back out, and it would show you a 3 by 3 matrix that looks exactly like what we just did there. Then I would do what? I would just write out determinant of A after that, and what you would see MATLAB would give you is it would give you minus 33. I encourage you to go ahead and try to do that. I'll just verify that that's something that makes sense to you. Rank. There is this idea of rank in linear algebra. It tells us how many linearly independent rows or columns there are in a matrix. And so we aren't going to dwell on this too much. It is a concept that I think you should be familiar with. We aren't going to make huge use of it, but let's just go ahead and demonstrate it by example here. If I had a matrix 1, 2, and 2, 5, those two rows are linearly independent from one another. You can't make any of those rows as a linear combination of the other rows. And so this one is a case where the two different rows are each linearly independent from one another. So the rank is going to be equal to the number of linear independent rows, 2 in this case. If I look at another matrix, another example where I have a 1, 2 and a 2, 4, in this particular case, they are not linearly independent rows. How would I know that? Go ahead and take this first row, that's a 1, 2, right? And multiply it by 2, okay? I'm just scaling the overall row. What do I end up getting? I get 2 and 4, which matches that bottom one. I can get the second row, right, as just a simple combination of a scalar times another row. If it was a bigger matrix, it would be some combination of scales and sums of other rows. In this particular case, it's really easy to see that the second row is a simple multiplication of an upper row, so they are not linearly independent rows. There's only one linearly independent row in this, so the rank is going to be 1. Again, MATLAB would make this really easy. If you were going to want to do this in MATLAB, you could just say rank, and you would put in your matrix A, whatever it was, in this case 1, 2, 2, 5, or 1, 2, 2, 4, and you would see it spit out those numbers, 2 and 1, easily verifying this. Okay, let's talk some operations between either vectors or matrices, and we'll start out with the most basic operation of addition. If I take a linear algebra object A, and I add it to another linear algebra object B, let's just call them matrices because we know vectors are special cases of matrices, so by calling it or dealing with matrices, we're actually covering all of it. If I take a matrix A plus a matrix B, for us to be able to add them together, there is a requirement, right? It requires that A and B have the same dimensions, because addition between matrices is always done element by element. What do I mean by that? Corresponding elements between these two objects are added together. That's how we add matrices. So they must keep the same dimension. MATLAB will absolutely yell at you if you try to add a matrix A that was a 2 by 2 and added it to B, which was like, let's say, a 3 by 3. It wouldn't know how to do it because it wouldn't know how to element by element add these up together. B in that case had a lot more objects than A. It wouldn't know what to add to them. So if you are trying to tell MATLAB to do an operation where things are inappropriately sized, MATLAB will yell. I will say that probably, I don't know, far more than 50% of the errors and struggles I see of students in trying to debug MATLAB code or get MATLAB code to execute appropriately is because they're asking it to do linear algebra-like operations, things like addition or multiplication or whatever, and they aren't totally paying attention to the dimensionality requirements to do those operations successfully. So if you're getting a lot of errors in your MATLAB code as you go along, that's one of the first places I'd check. I'd make sure that the objects that I'm adding have the right kind of dimension and that the way that I'm doing those operations is appropriate for those sizes. So let's go ahead and do an example of this. Here's an example. I'm going to go ahead and take a 2 by 2 matrix, 1, 2, 3, 4. I'm going to add it to another 2 by 2 matrix, and that's going to be 5 minus 6, 7 minus 8. And I should get the result, which has the same dimension. It's also going to be a 2 by 2. How do I get these results? I'm going to take corresponding elements. So here's a 1 in the upper left. I'm going to add it to the 5 in the upper left of the other one. That gives me a 6 in the upper left of the result. Same location elements added together to give me the same location result. If I do that across the board, I get that whole result off on the right. For example, the lower right, I would take a 4 minus 8 is going to give me minus 4, and the rest fall through just in the same sort of way. To illustrate this idea that not paying attention to the sizes, if I had a case here, 1, 2, 3, 4, and I tried to add it to a 5 minus 6, 0, skip down to the next one, 0, 7 minus 8. What is this? This is a 2 by 2 matrix, and this one is a 2 by 3 matrix. Because these dimensions are not equal to one another, you would get an error in this case. MATLAB would error out. This is not a well-defined or an appropriately defined operation between these two objects. They are not sized in a way that addition makes any sense. So you would always get an error in this. Subtraction is just a special case of addition, so it would require the same sort of requirement that the two objects you subtract have the same size and the result is the same size as those objects, and you just do corresponding element. It's an element by element subtraction. We don't really have to go through that. Let's talk multiplication. Multiplication is the next step up, right, from addition. And actually, if we can do addition and multiplication, we're doing pretty good. You can do a lot with multiplication and addition. It turns out, though, multiplication is a little more complicated because there are definitely competing ways that are necessary or of interest to us in thinking about how we define multiplication. And we might still call them both or all of these operations multiplication-like. We're going to talk two forms of multiplication that involves matrices. And the first one I'm going to talk about is matrix multiplication. So this is multiplication as defined in linear algebra. So I'm going to look at an object, A, vector, matrix, whatever you want to do, and I'm going to multiply it by another matrix, B. Straight multiplication, matrix multiplication, if you will. We're going to multiply these two guys together. The requirement for matrix multiplication is that A and B be what is called conformable. Mathematical terminology here, this conformability really is just saying something about a dimensionality requirement between A and B. Here's the way you probably saw it in linear algebra and the way that I think most people are introduced to this. Object A does have a dimensionality. It's some m by n, right? M rows by n columns. B has also got some dimensionality. Let's let it be generically defined in terms of some p number of rows and q number of columns. If we are going to multiply A times B, right, the number of columns of A has to match the number of rows of B. So if I put those guys side to side, they usually just circle those guys together. So they circle those two interior dimensions, and they say that those have to be equal. N has to be equal to P. If you do not have this, you cannot matrix multiply them. So A and B must be, right, conformable. The number of columns of the first has to equal the number of rows of the second. I think we can understand why this particular requirement is needed by going through an example. I would also say that when we take that kind of interior equality, so when we look at that M or that N being equal to P, that's the requirement so that the multiplication can occur. What's the dimensionality of the result? Well, if you look at those remaining dimensions, that M and the Q, that actually will tell you the resulting dimension. So the result is an M by Q result. So let's go ahead and show this by an example. Let's go ahead and take a look at the example here where I've got a 2 by 3 matrix. So this is an original guy that is 2 by 3, right? I've got 2 rows and 3 columns, and I'm going to multiply that by a 3 by 1 column vector. Because the number of columns of the first object, there's 3 of them, equals the numbers of rows of the second object, there's 3 rows, these two objects are conformable, and that means that I can matrix multiply them. The result will be a 2 by 1 vector, right? A 2 by 1 vector. So it'll also be a column vector, but there will only be 2 elements in it. How do I carry out this operation? If you remember back from linear algebra, I'm going to start out with my top row here, right? And I'm going to basically take all of the elements of that top row, and I'm going to multiply them element by each of the elements of that first column on the next, right? And add them all together. So I'm going to take this 1, multiply it by that 2. I'm going to add that to this 2, multiplied by that 1, and I'm going to add it to this minus 2 multiplied by that minus 1. All of those guys multiplied together and added together will give me the first result, okay? So in this particular case, 1 times 2 is 2, 2 times 1 is 2, minus 2 times minus 1 is 2. So when I do each of those element multiplies and then add them all together, I'm going to get 2 plus 2 plus 2 is going to give me a value of 6. If I jump down to the next row, I'm going to just keep doing this for each row involved in there, right? I end up getting the same sort of structure. I'm going to get 3 times 2, that is 6, minus 1 times 1, that's minus 1, and 2 times minus 1, that's minus 2. Add those guys all up together and I get 3. So the result of this matrix multiplication, right, is going to be the 2 by 1 vector of 6 and 3. If there had been, let's say, another column over here, what would the basic procedure be? I would take this first row times this first column. That would have given me this first element over here. I'd take that first row then again times the second column, and that would give me an answer over here. Then I jump down to the next row. I do that row, first column, that would give me a value just like that, 3 there, and then I do that row again, right, times that second column, and that would have given me something over there. Then I would have gotten a 2 by 2 result. So hopefully this reminds you a little bit about a process that you had studied before in linear algebra. Again, MATLAB makes this super easy to test. So if I called this first thing A and the second one B, as we had done when we first introduced this, if you had A and B defined, you could just in MATLAB say A star B, A times B. If you just use the regular multiply symbol that you probably have seen in numerous occasions, MATLAB defaults to seeing that star to mean matrix multiplication. If I look at an example of where I would get an error, I'm going to take those same objects I looked at before, right? So I'm just going to interchange the order. So I'm going to take, instead of A times B, I'm going to do B times A here in this case. So I have now a matrix that is going to be this column vector, 2, 1, minus 1, and I'm going to try to multiply it by this 2 by 3 matrix that has a 1, 2, minus 2, 3, minus 1, 2. Okay, I'm just interchanging the order there. If I look at the dimensionality, the first one's a 3 by 1, the second one is a 2 by 3. When I take a look at those interior dimensions, the 1 is not equal to 2. That means they're not conformable, and that does mean that I'm going to get an error in this particular attempt at matrix multiplying these two objects. Notice, we can see really easily in this particular case that A times B, matrix multiply, right, does not always equal B times A. In fact, it's rarely the case that they are equal. When you're studying real numbers back in high school and the like, or even complex numbers, we talked about a property of commutability in both addition and multiplication. It didn't matter what order you multiplied two real numbers or two complex numbers. It didn't matter which order you multiplied, added, doesn't matter. For matrices, that idea of commutability in multiplication no longer holds, right? And so knowing that can save you some errors as well. I'm going to again make that statement that I see students all the time, and myself actually every once in a while. I lose track of the dimensionality of an object, and I tell MATLAB to multiply them. So I might do something like this guy times this other guy, and MATLAB will scream error. And a lot of times we're sitting there trying to figure out where that error goes. If you just pay attention to this error set from MATLAB, you can get really good about trying to find out, or it's a good place to start looking. The vast majority of errors that I see people doing is because they are not using appropriately sized objects for the operation of interest. A matrix inverse, right, is a matrix such that when you take the original matrix times its inverse, you should get the identity matrix. So A inverse, right, is a matrix such that my original matrix A times its inverse gives us an identity matrix. We know something about multiplication. We know multiplication has to have conformability. So let's just think dimensionality here. If A was an let's get rid of that little piece and try this again. If A was an n by m, in order for me to multiply this by anything, the inverse would have to be m by something. And it's always going to be something like an m by n, and that will give us a result n by n. So an inverse matrix, right, is going to have the same dimension as the transpose of the original object. And so when I multiply something by its inverse, I'm going to get something like that n by n dimensionality, something along those lines. You can review it's a tedious procedure in a linear algebra book if you like, but really for us in what we need to do, we're not focused in this particular class on worrying about the dynamics of hand calculating matrix inverses. So we'll really just use the MATLAB built-in function inv, which allows you to compute a matrix inverse directly. Multiplication. Multiplication can also take the form of what is called element by element multiplication. In the case of element by element multiplication, what are we saying? We're going to have an object A and we want to multiply it by B such that corresponding elements in those two objects are multiplied together. That's it. Just like addition. It's kind of like a multiplication version of the element by element addition that we've seen before. There are a lot of applications that require multiplication in this way rather than multiplication in the matrix way. What would that require? It requires that A and B have the same dimension. If A and B have the same dimension and they weren't square, right, you could never matrix multiply them. That would not be conformable objects and you would get an error. In the case of element by element, right, they just have to have the same dimension, just like addition requires the same dimension. The result will, of course, also have the same dimension because we're going to just do it element by element. We need a way of indicating this kind of operation and distinguishing it from the matrix multiplication. And I'm going to use here a little notation that is consistent with MATLAB. I'm just going to put a period before that star, so it's a dot multiply. And at least in a program like MATLAB, a dot anything generally indicates, not always, but generally indicates element by element type operation. So a element by element multiplication would be dot star, an element by element division would be dot slash, an element by element exponentiation would be dot with that caret symbol. So that dot preceding an operator oftentimes will make it element by element. I do see students sometimes do something like this. They put a dot plus because they want a element by element add. That's redundant. It's not necessary because adds are always considered element by element. So really that's just indicating a lack of understanding of the basic requirements for operations. You'll see the dot notation used mostly in this class or most basic linear algebra operations as a dot star, a dot slash, or a dot caret, right? So dot multiply, dot divide, and dot powers, something along those lines. How do we carry out this operation? You just multiply corresponding elements. Let's do a couple examples. Here I have a vector 1, 2, 3. This is a 1 by 3 object. I want to element by element multiply it by 4, 5, and 6. If you look at the dimensions here, a 1 by 3 and a 1 by 3, they are not conformable, right? So I could not matrix multiply it. If I left off that dot, if I got rid of that dot in there and just put a star and did that in MATLAB, MATLAB would yell at you. It wouldn't know how to matrix multiply those guys. Putting the dot in there says we're doing multiplication in a different way. We're doing it element by element. So if I look at the overall dimensions 1 by 3 and this other guy's overall dimensions 1 by 3, those guys are the same. And so I can do this element by element. How do I carry out the operation? I take the first one and take it times the first one of the second object. So 1 times 4, that gives me 4. Next one over is going to be a 2 times 5. 2 times 5 is 10, so I should get a 10. And a 3 times 6, that's going to give me 18. The dimensionality of the result matches the dimensionality of the original two objects. So we already made this comment before. MATLAB uses things like multiplication, division, and exponentiation, generally default in a matrix sense. We haven't even talked about matrix exponentiation. We don't need that for this class. We won't worry about it. MATLAB uses dot star, dot slash, dot caret to be element by element versions of those operations of multiplication, division, and exponentiation. I will say that in this class, right, most often we are interested in element by element type operations. Why do I say that? Well, consider something like this. Suppose I had a signal x of t, and I want to multiply it by another signal y of t. We are going to represent something like x of t as a vector of a bunch of values for all the different values of time we're interested in. We want to multiply that by another signal, and what we want to do is we want to multiply corresponding values of these signals. So it is naturally an element by element kind of operation, element by element multiplication. So in many, not all, but many, if not most of the cases that you will likely use MATLAB in this class, we're primarily going to be looking at things from an element by element operation. And I think what I oftentimes see is that many of the mistakes that come in people's code that keeps it from running is people just erroneously or kind of forget that dot in there. When they're trying to carry out an element by element operation, they forgot the dot, and that makes it not work out. Last one I think that we're going to deal with here in this linear algebra review is something called Cramer's rule. This is a useful technique for solving a set of linear equations. So let's go ahead and look at the matrix representation of this. So I can have an equation like this, a matrix A times a column vector X being equal to another column vector Y. Many problems can be cast in this structure, and oftentimes what happens is we have a known matrix A, right? And we have an unknown vector x, and then we have a known set of values that that product is equal to. They oftentimes call that the observation vector. And what we want to do is we want to be able to solve for x. We want to be able to solve for this guy. We want to get x all by itself. Well, if we think about how we might want to do that, we need to somehow get that A to the other side. We know that there's a bunch of stuff, right, that ends up making this difficult. I guess in a linear algebra sense, you could multiply on the left, and you have to worry about direction here, by A inverse on each one of those sides, something like that, right? This thing now is going to give me the identity matrix times anything should just give me the anything, so that should just return X. So this guy should be the solution. If you have MATLAB, that's easy to do. You can go inv A times matrix style multiplication, the vector y. That certainly will do it. We're just going to show how you can find a particular element of the vector that you're trying to find. So you could do this across all the different elements in X. And Cramer's rule says it's something like this. The ith element of X that you're interested in can be gotten by 1 over the determinant of A times the determinant of an augmented matrix that comes from A, where I replace the ith row, right, of column A replaced by that observation vector Y. Again, this is not a linear algebra class, so I'm certainly not going to prove this. We're just going to take a technique that you should have studied before and that is established well in mathematics and be able to use it. So let's demonstrate this by an example. And this is something that actually we do need some ability to do. Oftentimes in this class, you'll be able to just do it through matrix operations in MATLAB, and you won't have to go through all the hand steps, but I think you should be familiar and able to do the hand steps. So let's go ahead and look at a system of equations here, something along those lines, where I've got a matrix 1, 2, 3, 4 multiplied by a column vector x1, x2 being equal to a set of observations 5 and 6. By the way, I think we saw something like this earlier in the lecture. Let's see if I can find that guy. I think we had something in here that involved trying to find a solution from a pair of expressions. I'll see whether or not I can find it or not. I thought we had one in here. I think it had to do something with those PFEs. Did we have it in this lecture? Maybe it was the previous lecture. I know in one of our lecture examples, we had a case where we had a system of equations and we needed to solve that system of equations. That would easily be accomplished using this particular technique of Cramer's rule. Okay, I didn't find it. We'll see if we can find it. This example will still serve its point. So I have this series of equations. There's 2 equations and 2 unknowns. Actually, if I broke this up, right, if I went ahead and expressed this not in a linear algebra style, what would I get? I would get 1 times x1, that would be x1, plus 2 times x2, so plus 2x2 being equal to 5. That's one of the equations. I can just multiply that matrix 1, 2, 3, 4 times that vector x1, x2, and on the left-hand side, the first part of that would be x1 plus 2x2 being equal to the first thing on the right-hand side, that's a 5. Do it for the second part, I'm going to get 3x1, right, and I'm going to have plus 4x2 being equal to 6. So I have 2 equations, 2 unknowns. It is linear in those unknowns, and we can express it in this linear algebra notation. Part of the advantage of that is it makes it systematically possible to find this unknown vector x1, x2, and if it was a 100-element one, you could do it even for 100 elements. We're going to go ahead and apply Cramer's rule here. I want to find x1 first, and so if you go back here and look at what I need for x1, I'm going to take 1 over the determinant of A, that's always the same, and then I'm going to augment that matrix A by replacing the first column because I'm looking for x1. First column is going to be changed by using that observation vector y. So let's see if we can do that. A was 1, 2, 3, 4, so I'm going to need the determinant of A and divide that. So 1 over the determinant of A, I'm just going to throw that in there. And then I need the determinant of this kind of modified matrix. So what is the modified matrix? We look at A, right? But we are going to take the first column, that's 1 and 3, and we're going to replace it with the y column, 5 and 6. So I get 5 and 6, and then I leave the rest of it alone, and there's only one other column left. That's just the 2 and the 4. So I need to carry out a couple of determinant operations in order to do this. For the numerator, the determinant of this guy, right, is going to be 5 times 4 minus 2 times 6. So that's going to be 20 minus 12. That's going to be 8, something along those lines. The determinant in the denominator, that's that determinant of 1, 2, 3, 4. That determinant is going to be 1 times 4 minus 3 times 2. That's going to be 4 minus 6 or minus 2. So I have 8 over minus 2, that is minus 4. So x1 is equal to minus 4. Same process for finding x2. The determinant in the bottom doesn't change. That's still determinant of A, so that's a determinant of 1, 2, 3, 4. The numerator determinant does change because I'm looking for the second coefficient, x2. I'm going to change the second column, right? I go back to my original A. It had 1 and 3 in there, so those stay the same. The second column, right, which was originally 2 and 4, is going to be replaced by that observation vector of 5 and 6. So the bottom here is the same. It's still 4 minus 6. The numerator changes. The determinant here is 1 times 6 minus 3 times 5. So 6 minus 15 gives me minus 9 over minus 2. That is 4.5. You could certainly verify this through MATLAB. There's a lot more in the book. I would suggest that everybody give it a quick read. The chapter does conclude with a bunch of just interesting and useful math facts. I think you'll find those of interest and use as you go through the semester. Sometimes just needing like an integral or a derivative of some function you might have forgotten. There's a lot of useful information in there. Next time we will start chapter 1.